Today we will be taking solid state chapter. See, in this solid state, generally in what areas the questions frequently come. One is how many atoms are there in a unit cell. First of all, what is unit cell? Let me just briefly explain. Suppose if there is a big building is there, and in that many rooms are very orderly arranged rooms are there. So all these rooms, suppose there is a room here, left side room, right side room, back, front, up, down, like that. Imagine rooms are there in all directions. So like that, a building is packed with several rooms, and this total building is called crystal lattice. In terms of solid state, it is called crystal lattice. Now each room in that building is called unit cell. So in a crystal lattice, let me imagine it as a building of the solid. Now in that each room is like a unit cell. So unit cell is the smallest repetitive unit which creates the entire crystal lattice. Okay. Now, so one model of question what you can face is how many atoms are there per unit cell of the lattice. Second, what is the coordination number? Means how many nearest neighbors are there. And third, what is the volume of the unit cell? So these kind of questions comes frequently in the this competitive exams like EAPCET, and also how to find the density of the solid. So all these points now today we are going to discuss, and we will solve several problems also on these topics. Now first we will see number of atoms in a unit cell. See, normally in our syllabus, three types of unit cell we will come across. One is simple cubic, body centered cubic, and face centered cubic. First of all, let me just briefly explain what is simple cubic. See, suppose a cube is there. Simple cubic means there is a cube. Now in this cube, let's say this is the smallest repetitive unit in that entire crystal lattice, smallest room. Now in this unit cell, if atoms are present only at the corners, like this, if only they are present at the corners, atoms are actually, we will imagine them as spherical, but for the sake of clarity, we will represent these spherical atoms as a points, which are called lattice points. So imagine these are the 8 points are there. Each point is at each corner of the cube. So 4 above, 4 below. Now like this 8 atoms are there arranged in this manner. Now, this is called simple cubic or primitive cubic unit cell. This is the basic. That's why it is called primitive unit cell. Next, two more are there. Second one is body centered cubic. Body centered cubic means these all 8 atoms will be there first similarly at the corners, plus one atom at the center of the body, means center of the cube. So in the solid crystal lattice, in a repetitive, smallest repetitive unit, if you focus, there 8 corner atoms will be there, plus body centered also, center of the cube also if atom exists. Such unit cell is called body centered cubic unit cell. If there is no center at the body, only corners, it is simple or primitive cubic unit cell, like that. Next, third one is face centered. Names itself suggest us where atoms are present. Face centered cubic unit cell means what? 8 atoms will be there at the corners, that is anyway common, plus centers of the 6 faces. Cube has how many faces? Left, right, front, back, top, bottom. Total 6 faces will be there. At each face, center of each face, there is an atom. So like that 6 face centers will be there apart from the 8 corners. This is called face centered cubic. Simple cubic, only corners. Body centered cubic, corners plus center of body. Face centered cubic, corners plus center of each face. There are 6 faces in a cube. Now, so in these are the 3 important unit cells. Now, in these unit cells, how many atoms are present per unit cell? That is the one model question you may get. So, let us focus on that first. First, primitive cubic unit cell we will see, and we will see how many atoms are there per unit cell. You may say, sir, you have already explained, so each corner has 1 atom, means there are 8 atoms are there in the unit cell. Done? No. See, here 8 atoms are visible here, but each atom is not entirely present with in a unit cell. They are shared with other unit cells also. Suppose this is the corner atom. Okay, this I am focusing here. Let's say this is the one corner atom. Focus on that. Now it is not present only for this unit cell. This is also corner for the other unit cell. Okay, and also there is a unit cell front side of this, and again adjacent to that. So this is the corner for the 4 same level cubes. You can put 4 cubes together, and that will be the same corner of those 4 cubes. And also that will be the top corner of the same 4 cubes, similar 4 cubes. And as well as if you place the cubes above it, it will be the bottom corner of the other 4 cubes. So each corner atom here actually shared between 8 unit cells. For 4 cubes it is a bottom corner, for 4 cubes it is a top corner. 8 cubes share the same corner atom. Like that, every corner atom, here 8 atoms are 8 corners are there. So these 8 atoms, each atom is shared between 8 unit cells. Okay, keep that in mind. See, that is visible here. See, suppose as you see here, there are many cubes are there. If you notice here, there are how many cubes are there? There are 8 cubes are there actually. So for 8 cubes here, this atom, for 4 cubes, if you see 1, 2, 3, 4, for 4 cubes it is the top corner, and for 4 cubes it is the bottom corner. For above cubes, 4 cubes, it is the bottom. So it is actually shared between 8 unit cells. Now, since it is shared between 8 unit cells, per unit cell its contribution is 1/8, because divide it into 8 equal parts. Then per unit cell, how much portion you will get? Only 1/8. So each corner contribution is how much? Only 1/8. Like that, how many atoms are there? 8 atoms are there. 8 corners, 8 atoms. And each contribution is how much? 1/8. So net atoms per unit cell. Take only 1/8 portion of each corner atom. 1/8, 1/8, 1/8, 1/8. 4 corners above. Again 1/8. Like that, if you take 8 atoms, 8 corners, each contribution 1/8, net value is 1 atom. So per unit cell, only if you combine all corners, net atom is 1. So this is the way you have to calculate. See, this is the 8 corners. Actually, these 8 spheres are packed like this. So each sphere we represent as a point for the sake of clarity, which is called lattice point. So actually, these 8 spheres are packed like this, and if you join them, you will see a cube forming them. But each atom we represent as point here, like that. That's why this figure is coming here. Now, if you take only 1/8 portion from each corner, see, only 1/8 portion is only there here. So if you join all these 1/8 portions, 8 portions of like that, you will get 1 atom, equivalent to 1 atom. This is the old NCERT text. Actually, in new NCERT, when they revise this solid state is removed. I hope you are all having this old NCERT. At least for revising this P block, you must have bought. So in that old NCERT textbooks, solid state chapter is also there in the second year, we go through it. So this from that chapter only I have taken the pages to explain here. Next, body centered cubic. See, body centered cubic also, see, there are here 4 corners above, similarly 4 corners will be there below, and at the center of body, can you see this one? Body center, this is the center of the body. So there are 8 corners occupied by the atoms plus center of the body also. Now for 8 corners we know how much contribution for each corner, 1 by 8. So each of the 8 corners, 1 by 8. Center of body is completely present within the cube. It is, if there is an atom within the cube, it is not shared with any other unit cells. It is entirely present within that. Therefore, contribution of this is 1. So 8 corners, contribution is 8 into 1 by 8, that is 1 atom, plus 1 body center atom is there, it is entirely present within the unit cell only, its contribution 1. If you add these two, total atoms are 2 per unit cell. Which unit cell? Body centered cubic unit cell. In simple cubic or primitive cubic, only 1 atom per unit cell. In body centered cubic, 2 atoms per unit cell. Next, third, face centered. As I already explained, face centered has corners plus center of the faces. See, suppose if you take, these are the four corners, top corners of a cube. If you visualize these 4 atoms, see, this is the center of that 4 corners. Top face if you take, that is the center of the face. Like that, every face has a center. Like that, 6 faces, 6 face centers exist. And corners contribution per unit cell we are already aware of, 1 by 8. And what about the face center contribution? Each face center, suppose there is a wall, imagine, see here, this is the, let's say this is the face center atom. This is 1 unit cell, this is 2nd unit cell. For both of them, this is a common wall, common face, and at the center of the face, there is a atom. Now, this atom is shared between 2 unit cells, adjacent. So, per unit cell, its contribution is half. Half here, half here. So, each face center contribution is 1 by 2. Now, see. So, each face center corner contribution 1 by 8. So, 8 into 1 by 8, 1 atom for the all 8 corners. 6 face centers are there. Each contribution is how much? Half per unit cell. So, 6 face centers, 6 into 1 by 8, 3 atoms. So, net how many atoms per unit cell? 1 plus 3, 4. So, this you remember. Face centered 4 atoms, body centered 2, simple cubic 1. I am summarizing these points here. See, number of atoms per unit cell, simple or primitive cubic. How many? Since only 8 corners are there, 8 into 1 by 8, answer 1. Next, body centered cubic unit cell. Here 8 corners are there, plus center of the body entirely present. So, total 2. Face centered cubic, which is also sometimes termed as cubic close packing, CCP. CCP or FCC. Face centered cubic is written as FCC. Body centered cubic is written as sometimes BCC. So, FCC or CCP both mean the same. In such scenario, 8 corners plus 6 face centers, total how much? 4 atoms per unit cell. So, atoms per unit cell is this. You must remember this. Next. relation between edge length and radius of atom. See, here what is the cube? Cube has the edge length. Let's call it A. And radius of atom is R. So what is the relation between A and R in each case? So here A is equal to 2R. In case of simple cubic, edge length is equal to 2R. In case of body centered cubic, root 3A is equal to 4R. I am not going into the derivation part, which can be derived from the structures. From if you visualize the spherical atoms in a cube, from that you can get these relationships. Just remember these relations, it is sufficient. At this stage, there is no need of learning through the derivations of these relations. Just remember the relations, that is sufficient to answer the problems. Next, face centered cubic relation, root 2A is equal to 4R. So simple cubic, A is equal to 2R, body centered and face centered, root 3A. But there 4R, here root 3A is equal to 4R, face centered root 2A, not root 3A. Root 2A is equal to 4R. Next, one more area where you will get question is coordination number. Means what? Number of nearest neighbors to the atom. So here in simple cubic, number of nearest neighbors. How many nearest neighbors are there in simple cube? There will be 6 nearest neighbors. For example, if there is an atom is there, left side atom, right side, top, bottom, front, back, like that, nearest neighbors are 6 will be there actually, back, front. Anyway, just remember the number. Body centered cubic will be 8, face centered cubic will be 12 atoms, nearest neighbors. So 3 areas we have gone through here today, now as of now. One is first is number of atoms per unit cell, second relation between edge length and the radius, A and R, third coordination number. Simple cubic, number of atoms 1 per unit cell, relation A is equal to 2R, coordination number 6. Body centered cubic, how many atoms per unit cell? 2. And relation between A and R, root 3A is equal to 4R. Next, coordination number 8. Face centered cubic, number of atoms 4 per unit cell, and A and R relation, root 2A is equal to 4R. Coordination number 12. Next, voids. Voids means empty spaces. Empty spaces in CCP, I already mentioned CCP or FCC both mean the same. Cubic closed packing is same as face center cubic. In that, voids you need to be aware of. Number of octahedral voids. See, octahedral voids, there are 2 types of voids exist in this FCC or CCP, that is octahedral, tetrahedral voids. Depending upon the shape of the void, there are 2 types, octahedral void, tetrahedral void. Now, octahedral void, how many octahedral voids will be there? Is equal to number of atoms. Number of tetrahedral voids is equal to 2 into number of atoms. Just remember this formulas. Tetrahedral will be double of atoms. Octahedral, how many atoms are there? In the unit cell, same number will be there, octahedral. For example, CCP, how many atoms per unit cell? 4. Per unit cell, 4. So 4 octahedral voids will be there, 8 tetrahedral voids will be there. Like that. CCP or FCC. And one more is there, HCP, hexagonal closed packing. Hexagonal closed packing, HCP we say. This is cubic closed packing. And HCP also there will be voids, tetrahedral, octahedral. 2 types of empty spaces will be there. There also same formula. Octahedral will be equal to number of atoms. To double is the tetrahedral voids. tetrahedral empty spaces. But only thing you have to remember is in hexagonal close packing HCP, number of atoms per unit cell is 6, whereas cubic close packing 4. This you remember, other points will be taken care automatically. Okay. Now see, a compound is formed by two elements X and Y. X, Y are the two things are there. Atoms of the element Y as anions. Y is anions, they are saying. Make CCP. They are actually creating the cubic close packing or face-centered cubic structure. So that means per unit cell, how many Y atoms will be there? 4. Just now we have discussed FCC or CCP. How many atoms per unit cell? 4. Okay. So Y is making the CCP. And those of element X, which are cations, occupy all the octahedral voids. The cations X is doing what? It is occupying the empty spaces. Which empty spaces? There are two types exist in CCP. It is occupying only octahedral because its size allows to fit there only. So it is occupying the octahedral. What is the formula of the compound? In such cases, find formula of the unit cell. It will be automatically formula of the entire compound. So unit cell formula is what? In unit cell, how many Y will be there? Y is making CCP, and in CCP how many atoms? 4 atoms per unit cell. So therefore Y is making the CCP means there should be 4Y. Now if Y is 4, what about X? X is occupying the octahedral voids. So number of octahedral voids, how many? Number of octahedral voids we know, which is equal to number of atoms per unit cell. Which atoms? CCP atoms. Whatever atoms making up the CCP lattice, how many are there? That many voids will be there. So how many atoms are there which are making up the CCP? 4 atoms. So octahedral voids also 4. And all these 4 are occupied by the X. So X4, Y4, which is simple ratio XY is the formula of the compound. So remember, first in such problems you see which atom is making the CCP or FCC. That atom, here Y is making CCP. So this Y element, how many atoms will be there per unit cell? 4. Because in CCP we have discussed 4. Now if 4 atoms are there which is making up the unit cell of CCP, then there will be 4 OVs, octahedral voids, double means 8 tetrahedral voids present there, empty spaces. So 4 octahedral voids X is occupying, so X4, Y4. Next. I'm seeing some questions here. What is the coordination number of FCC or CCP structure? There will be 12. Okay, and that's it. BCC has 8 coordination number, and simple cubic has 6, FCC has 12. Okay. Next, voids in HCP. I just mentioned in HCP, hexagonal closed packing, per unit cell of this hexagonal closed packing, per unit cell if you take, how many atoms per unit cell? 6 atoms. I am not going into the derivation part, just like simple cube, body centered, face centered. Just remember the HCP, how many atoms per unit cell? Atoms per unit cell, 6 atoms. In hexagonal closed packing. That means 6 atoms, net atoms 6 per unit cell of HCP. Now in that, empty spaces, how many will be there? When 6 atoms are present. OVs will be number of atoms, that means 6 only. Tetrahedral voids will be double, therefore 12. In hexagonal closed packing. And you may say, what about sir body-centered cubic? Body-centered cubic unit cell, how many atoms per unit cell? There are 2 atoms. Yes, there will be definitely empty spaces will be there, but those are not tetrahedral or octahedral shape. Those are different kind of voids, not comes under the tetrahedral, octahedral, which is not there in our syllabus also. And only we will get voids type of problems on CCP, HCP. Just remember these two. Now, so here B is forming HCP. HCP is formed by B, element B. That means per unit cell, how many B will be there? Per unit cell, number of B atoms, because B is making the HCP unit cell, and number of atoms of B per unit cell will be 6. Just now we have discussed hexagonal closed packing, 6 per unit cell. Now, next read the other things. And those of the element A, B is making actual building, actual lattice. In that lattice per unit cell has how many B's? 6. Now, there are empty spaces will be there in this building. In this empty spaces, what is occupied? A occupy 2/3 of tetrahedral voids. Okay. So, A occupying what? 2/3 of number of tetrahedral voids. I am calling tetrahedral voids TVs. What is the formula of the compound? A and B. Okay. So, first in this case, you just write like this, A, B. How many B are there per unit cell? Per unit cell, if you find formula, that will be same as the entire solid lattice. So, focus on unit cell, 6. And A how many? 2/3 of tetrahedral. How many tetrahedral voids will be there? If 6 atoms are there per unit cell, these 6 will create 6 octahedral type of empty spaces, double, 12. 12 tetrahedral types of empty spaces. So, 3, 4 times 4 to 8. So, A8, B6. Simple ratio is A4, B3. This is the formula. A4, B3 is the formula. Next, packing efficiency. So, packing efficiency means what? How effectively things are packed inside the solid. And its formula is volume occupied per the unit cell by total into 100. Suppose if I ask you what is packing efficiency of this room which I am in. Now, what is the volume occupied? That divided by total volume of the room into 100. That is the occupied percentage, which is called packing percentage. Same way, atoms occupy the unit cell. What is the volume of the atoms which is occupied unit cell, and total unit cell volume into 100. I will just derive for the simple cubic. Rest I no need to for derivation. Just I will write the final result. Simple cubic. In simple cubic, you know how many atoms per unit cell? 1 atom. So, first I will write number of atoms into 4/3 pi r cube, each atom's volume into total atoms. This is the entire volume occupied by volume of unit cell. In cubic unit cell, volume is A cube, because if A is the edge length of the cube, you know volume of the cube is A cube. This into 100. Now, in simple cubic, how many atoms will be there? 1, 4/3 pi r cube by A cube. into 100. Next, what is the A value? A value is, we know the simple cubic relation, A is equal to R. You have to substitute that A is equal to R and then simplify this mathematical relation. You will get finally 52.4 around percentage. So in simple cubic, around 52% is occupied. That means around 48% is empty space in the simple cubic. That is what it means. In the same manner, if you follow body centered, how many atoms per unit cell? 2 atoms. Imagine there are no cations and nothing present in the voids. Voids are empty spaces only. Just focus on the crystal lattice only. Nothing is occupied, no cations are there in the this void spaces. Then only we are calculating. So 2 atoms per unit cell of BCC, 4 by 3 pi r cube by A cube. And what is the A in the BCC? A is equal, do you remember? A is equal to 4r by root 3. BCC relation. Substitute here and simplify, then you will get around 68%. So like this, in FCC also, if you do similarly, you will get around 74%. FCC or CCP 74. In HCP also, it is a little complicated to calculate, but still you will get finally 74% only in HCP also. So these percentages you remember: body centered, simple cubic 52 around, body centered 68, rest two are high efficiency. Empty space is less here. 74% is packing efficiency. Next, density of solid. See, we know density formula is what? Mass by volume. Density formula is mass by volume. Now, if you find the density of unit cell instead of entire crystal lattice, take the smallest repetitive unit called unit cell. If you find the density of the unit cell in the solid, then it will be the same density in the entire crystal lattice, because uniformity will be there anyway. So if you per unit cell, if you calculate, that will be the same value for entire crystal lattice. So mass by volume. Now focus on the unit cell now. So unit cell has how many atoms? Let's say number of atoms is written as here, number of atoms per unit cell you take, and each atom has how much mass. Now we know molecular weight. Molecular weight is the mass of Avogadro number, means 1 mole of atoms. Molecular weight is what? Or actually atomic weight or molar mass. It's better to write molar mass because we are dealing with atoms. That means atomic weight, gram atomic weight. Molar mass is what? Mass of 1 mole of atoms, means Avogadro number of atoms. If Avogadro number of atoms mass is this, per atom mass is how much? Divided by Avogadro number. This is the mass of one atom, single atom. Like that, how many atoms are there per unit cell? Take that number of atoms per unit cell. If you multiply, this is the entire mass of unit cell. So what I am going to calculate is mass of unit cell by volume of unit cell, which is the density of the entire solid also. That's what I am doing. Divided by volume of unit cell. Now normally cubic only we will come across, simple cubic, body centered, face centered, cubic. Cubic unit cell volume is A cube, and in a hexagonal case such problems won't come, so we need not worry about density of hexagonal. The other three, simple cubic, the other three are cubic unit cell. For cubic we know the volume formula A cube, simple. Now we just simplify this one. So this I will write it as Z. Z means number of atoms per unit cell. That is how in our NCERT also alphabet is used. Same thing I am using. Into molar mass by Avogadro number into A cube. This is the formula of the density. And A cube depends on the type of unit cell. Simple cube case A is equal to 2R relation, body centered has A is root 3A is equal to 4R, like that it may change. And this is the formula. Z value also, simple cube has 1 atom per unit cell, body centered 2, face centered 4. We will solve some problems, then you will get idea on this. Okay, first see, copper is there, has FCC. FCC with edge length of X. Means edge length means edge length of cube means what? A, small alphabet A is the length of the cube. R is the radius of an atom. Okay. So this is the X is given. This is the edge length. What is the approximate density of copper? Gram per centimeter cube. Avogadro number is also given. So now see, atomic mass of copper is also given 63.5. So density formula we know, number of atoms into molar mass by cube. Number of atoms, how many in FCC unit cell? 4. Molar mass of copper 63.5 grams by Avogadro number 6 into 10 power 23. Then A cube. A edge length is given X only. So X cube. This is the density. How much you are getting this one? See, approximately I will take this as 60 so that I can cancel this. So if I take this as 60, then around 10 times. So how much you are getting here? 40 and by 10 power 23 into X cube. Okay. And one more thing we forgot here. See, X is given in angstroms. Now here, see, we have taken directly edge length as X. We have taken mass in grams, 63.5 grams, but we have to take this also in centimeter cube. Then only you will get answer in grams per centimeter cube, because they are expecting answer in grams per centimeter cube here. But we have taken X in angstroms. That is the mistake we have done. So keep this in mind. X has to be converted into centimeters, not meters. So we know 1 angstrom is equal to 10 power minus 8 centimeters. So here what we have to do? Actually X into 1 angstrom is 10 power minus 8 centimeters. This is the centimeters. A value in centimeters cube. So 8 into 3, 24, 10 power minus 24 and 10 power 23. You will get 10 power So simplify this one. So this is already 10 times, so 40 divided by 10 power 23 into X cube into 10 power minus 24. 10 power 23, 10 power minus 24 is 10 power minus 1. 10 power minus 1 if you take to the numerator 10, so 400 by x cube. So which is the answer closest to this? This is 42.3. This is 4.23. Okay, this is 423. So 4.23 is here, 423. 423 is closer to the 400. So answer is C. Next. A compound is formed from elements X and Y. The atoms of Y forms the CCP. So what is actually building the lattice? Y is building the lattice. So since Y is building the CCP lattice, per unit cell of CCP, how many atoms of Y will be there? 4. So that is the main thing we have to first figure out. Whichever is making the actual lattice structure, from that you figure out how many atoms per unit cell exist. Okay, so Y will be how many? 4. Keep that in mind. Atoms of X occupy half of the octahedral. Okay, they are not occupying full octahedral, only half. And half of tetrahedral also they are occupying. Okay, so look here, Y, X. Y is making CCP unit cell, so per unit cell 4 will be there. X, how many occupying X? First of all, how many OVs will be there? OVs will be in CCP 4, TVs, tetrahedral voids will be double 8. So is it occupying entire octahedral voids? No, half of it. So half of the 4 is 2. And tetrahedral voids also half only occupying, means 4. So 4 plus 2, 6 X atoms are at 6 places. So total 6 X atoms are there. So it can be written as therefore X6, Y4. If you write the simplest ratio, X3, Y2. This is the formula. Means X3, Y2. Next. Look here, if 0.5 mole of a metal forms hexagonal close pack, HCP this is now, hexagonal close packing. And in hexagonal close packing, number of atoms per unit cell are how many? 6. So therefore OVs will be 6, TVs will be 12. So 0.5 moles of metal is there. The total number of voids, how many total voids and tetrahedral voids in moles are. Okay. See, so hexagonal, how many atoms per unit cell? 6. Therefore, OVs will be same as 6. First, we will find out in 0.5 moles how many atoms are there, we will find first. Then same number of atoms OVs will be there, double will be TVs. Okay, we will do like that. So 0.5 moles if you take, how many atoms will be there in that 0.5 moles? 0.5 into Avogadro number. So 0.5 into Avogadro number is the total number of atoms present. Now OVs also will be same as the atoms number. So OVs will be, octahedral voids will be 0.5 into Na, and tetrahedral voids will be double of this means Na. Now answer the question. Total number of voids, how many? Total number means add these two. When you add 1.5 we will get 1.5 is the total. Number of voids, if you convert into moles by dividing with Avogadro number, 1.5 moles you will get. So moles only they are asking. So 1.5 moles total. Tetrahedral how many? Avogadro number. So moles wise 1 mole. So this is the answer here. An element forms a body-centered cubic lattice with edge length 300. The density of the element is 7.2. Number of atoms present in this. Okay. See, first of all, we'll get the idea. First, we'll think about how to calculate what is being asked. What is asked? Number of atoms present in this mass. In stoichiometry, mole concept, if such problem is asked, what we will do if you have to find number of atoms in certain grams? First, convert this mass into moles. Molecular weight or molar mass. This is the moles. Then atoms is equal to moles into Avogadro number. This is how we will do in stoichiometry chapter. Same procedure here. But only thing is, here molar mass M is not given directly in the question. We have to figure that out using the density formula of the solid state. See, body centered cubic, BCC they are saying. So let's apply the density formula. Density is equal to number of atoms. We know the Zm by Na cube. This is the formula. Now Z means how many atoms BCC has? 2 atoms. Molar mass. Molar mass only we need to find to substitute in this number of atoms divided by Avogadro number. Avogadro number also you keep like that only, because anyway here we need Avogadro number by M value to substitute. So don't simplify here, keep it Na only so that you can utilize here. Into A cube. A cube. A is how much? Edge length 300 picometers. And see, since density is given in centimeter cube, we will put picometers also, will convert into centimeters. Now 300 picometers. Pico means 10 power minus 12 meters. Okay. And 1 meter is equal to how many centimeters? 1 meter is equal to 10 square centimeters. So ultimately, if you multiply like this, you will get entire thing in centimeters. A cube. And then density also you substitute the value 7.2. Now you simplify this and bring M by Na value. M by Na you find out and keep it here. Means Na by M we want, just reverse it and keep it here. You will get the answer here. That is the procedure. And not tough calculation, because anyway 2 is there. This is also 3 cube 27. So 27 into 10 powers you will get. Bring it here and then take there. Then if you do solve it, you will get C option here as answer. Try it out later on. Next. The compound is formed by X and Y. Atoms of Y forms HCP. Means how many atoms will be there per unit cell? 6. Which atoms? Y. Y will be 6. Atoms of X are in some octahedral holes. Atoms of X, some octahedral, not all it seems. The formula of the compound is XY3. Okay, the formula is also given XY3. For every one X, there will be 3 Ys. What is the fraction of octahedral holes? Unoccupied. Unoccupied they want by X. Okay. First we will find occupied, then we will subtract from 1, we will get the unoccupied fraction. So first of all, how much X is present? See, Y is given as 6 per unit cell. How many atoms of Y? 6. X, How many X will be there per unit cell? It is occupying octahedral holes, and we don't know how many it is occupying octahedral holes. But they have given the formula. X is to Y should be 1 is to 3. So let's take per unit cell X is present n number of n number is present per unit cell, and X by Y ratio should be how much? N by 6. That should be same as the formula of the compound 1 by 3. So it seems there are 2 X atoms per unit cell. N is 2 means 2 X atoms are there per unit cell. And how many Y atoms? 6 atoms, because HCP, that's why. Okay, now let's calculate the fraction of occupied. How much fraction occupied? Here 2 atoms are there per unit cell. Fraction of octahedral voids I am calculating. How many total octahedral holes will be there? Same as number of atoms. So if 6 atoms are there per unit cell, octahedral will be 6, tetrahedral will be 12. So total 6 octahedral. Out of that 6, only 2 are presently occupied. That's why 2 are present in this formula. So therefore 1 by 3. This is the fraction occupied. But in the question they are asking unoccupied percent, unoccupied fraction. So fraction of unoccupied octahedral holes is equal to 1 minus, occupied is 1 by 3. So unoccupied fraction will be 1 minus 1 by 3, which is 2 by 3. So which option, where is the option 2 by 3? Option B has 2 by 3. This is the answer here. Again similar question, see, metal oxide crystallizes in hexagonal. Again HCP. And who is making the HCP? Oxide ions. So there will be, how many oxygen atoms will be there per unit cell of HCP? 6. Just keep on coming here. Many times I have explained. HCP, who is making the HCP lattice, that element will be 6 per unit cell. So here oxygen is making, so oxygens will be 6 per unit cell. I am finding out the formula of the unit cell, which is the formula of the entire solid. 2 out of every 3 octahedral holes occupied by metal ions. Now see, metal ions how many occupied? Not all octahedral. How many octahedral will be there? 6. Tetrahedral will be double, 12. Okay. So octahedral, 6 empty spaces, octahedral type of empty spaces are present, 6. Does all 6 are occupied by M? No. How many occupied? Oh, with 2 out of every 3, means 2 by 3. Meaning is 2 by 3 octahedrals are occupied. So there will be total OVs are 6, but all these OVs, octahedral voids, are not occupied. Only 2 out of 3 are occupied. Then just simplify it. First of all, if you take the ratio, 6 it cancels. So M2 by 3 O1 you will get. So M2 O3, if you put it in integers, M2 O3 will be the answer for this. Take the simple integer ratio, you will get that. If the side length of face-centered unit cell is 400, side length means what? A value. A value is given as 400. Radius of the metal in picometers is. Okay. So first find the relation between radius and the A value. Depends on the type of unit cell. Face-centered. Face-centered, what is the relation? Root 2A is equal to 4R. Therefore, R is equal to root 2A by 4. So root 2, A is how much? 400 picometers by 4. 400 times. So root 2 into 100. Root 2 you know 1.414. 1.414 into 100 is 141 point you will get. So this is the answer here. Next. This is a Bragg's equation related question, and for in the board exam preparations also, when you studied the solid state, you know the Bragg's equation. Bragg's equation is what? N lambda is equal to 2d sin theta. So here they have given second order line or 2.28. See, second order line means n value is 2 and angstroms, lambda is also given. D value is given 2.28 angstroms. Wavelength is what? Wavelength they are asking. This is question mark. And sin theta, the angle of diffraction. See, 2 theta value is given. So theta will be 45 degrees. So you take the theta value here, then you substitute and find the lambda. Next, see Frenkel defect. See, Frenkel defect and Schottky defect. These are two types of defects in solids. Frenkel defect means what? See, actually during the classes also I explained when for the board topics classes I have explained this Frenkel and Schottky. Very small difference is there. See, suppose if there is a cations and anions are present like this. Like this, in orderly fashion, cations and anions are present. Now, if cation moves from existing position to some other place, if it moves to some other empty space, then if it goes there and present there, that is called Frenkel defect. It is there inside the solid, but not in its original position. It went to some other position and stays there. That is called the Frenkel defect. Far away from home. It is there in the lattice only, but far away. And Schottky defect. Schottky defect means no way home. Means it's completely missing in the lattice. So if ions are missing in the lattice, that is Schottky. If ions go somewhere else and sit there instead of their original position, that is Frenkel defect. Now, in Frenkel defect, mass will be present there only. Mass is not decreased because the ions are present somewhere else, but in the lattice only. So mass no change, volume no change, density no change. In which one? Frenkel defect. In Schottky defect, since ions are missing, some ions completely missing from the lattice, mass decreases, but volume will be same because volume means entire thing you will take. Volume will be same, but in that mass will be missing. So density will be decreased in the Schottky defect. Now keeping this in point, now answer this. A metallic solid undergoes Frenkel defect. Its original mass, volume and densities are given. After Frenkel defect, after the defect, mass, volume and densities are given. Before Frenkel defect and after they have given values. The variations of M, V and D after Frenkel defect are, see, mass there is no change, volume no change, density also, therefore when mass and volume no change, density also no change. In Frenkel defect, this will be the case. In Schottky defect, mass will be lesser, volume will be less, volume will be same. If they give like this, then that will be the option for the Schottky defect, if they give like that. But anyway, here Frenkel defect case only problem is about only first option. So this is how you have to solve. So majority of questions come from the number of atoms per unit cell, density, A versus R relations, and this kind of number of atoms per unit cell. These are the areas where you generally face the questions. Packing efficiency, these are the areas. So now you just revise all these points once again and solve a couple of 5 to 10 problems on this chapter. Take the previous year's questions. 5 to 10 problems is sufficient to get the idea of how questions are being asked. That's it.